My name is Hewraz, and I'm a software engineer working at Cisco. I'm currently working with architectural support for NSO, but I also have a background in writing services and packages for NSO and for different use cases in different projects. In this presentation today, I'm going to talk about some of the best practices using Nano services, LSA, and commit queues. And I'm going to finish off by showing a small demo of an example that I've written trying to follow the best practices. Using Nano services, LSA, and commit queue can be a bit difficult on NSO. It introduces a lot of complexity and a lot of parameters you have to consider. What this essentially will introduce, in particular with commit queues, but also potentially with Nano services, is that you will get an asynchronous system. Let's look at this example. In a normal case, when you have a normal service without any commit queues, everything is synchronous. You get the network-wide transactionality. You commit something, everything happens in one transaction. Once your transaction returns, you know that everything is okay. Our configurations has been pushed to my network or it has failed. But when you introduce commit queues, you also introduce asynchronicity. So if you look at this example, we see here that I'm creating a service, I'm committing my service, and I get some commit queue information in return. Do I know if this has been updated or not in my network? Not sure. Without commit queue, I would know that once it's returned, it's updated in my network. But now I look at the commit queue. I see, okay, my commit queue is still executing. So my network hasn't been updated yet, even though my commit returned. But my intent is in the database. Or if we look at the delete scenario. So if we delete the same service that I just created previously, same thing, I commit something, the commit returns. But if I look at the commit queue, I have a commit in the queue. So my changes hasn't been pushed to the network yet. In this case, however, my intent is gone. So I don't even have a reference left to my service. What happens if my commit queue item fails? Well, then you're in a bit of a pickle. Now, if you look instead in the case where I change my service to a Nano service, and we look at the delete case again, I delete my Nano service, I commit it, I look at the commit queue, I see that I have a commit in the queue, I see that my intent is gone, so I don't have this as a reference anymore to my commit queue item, but I do have a zombie reference. And I can use that to monitor the process of the delete. This brings us to our first best practice, and that is to use Nano services. Nano services gives you a declarative way of designing your services. You can use your Yang model to see the flow of your service instead of having going through the code. So that is a benefit you get from Nano services. Another benefit is that your Nano service can handle the delete case, which is what I showed you previously. The plan data is also a good thing. You can use that to monitor the progress of your service once you've created it. You can see where it's at, how long it has gotten, and what's left, which preconditions are not met, and so on. And it's also, with this, easier to deal with commit queues, not only on the delete case, but also on the create case and the update case. So now that you've decided to use Nano services, the first thing you want to do is create your custom service operational data. A Nano service gives you plans out of the box. You can use this to monitor the progress of your service. However, a Nano plan will not update or will not change on an update. If you make a modification to your service, which will change the outcome of your service, you won't see this being reflected in your plan unless there's a precondition that is changing this. So only updating your service will not make any changes to your plan. So you can't use that to monitor the progress of your service on an update case. So for this, you will have to create your own custom model. And in particular, if you're using commit queues, you might want to see the status of your devices. You commit something towards the devices, it will end up in the commit queue. You might want to see this through your services. Is my commit queue executing? Has it finished? Or whatever status it is in. So putting this under your custom operational data is a good idea. And if you use LSA, you might want to populate this by using notifications. So you can read notifications that comes from your RFS, and you can put the relevant information into your custom service operational data. There are a lot of good built-in notification streams by NSO, giving a lot of relevant data, but you can of course create your own custom notifications as well. And now that you have created your own operational data, you want to put this outside of your service and not under your service. Because if you put it under your service, then the operational data will be deleted together with your service once you delete your service. Because if you delete your service, and everything under it will obviously be deleted. So if you put your operational data somewhere else rather than under your service, it will remain once you delete your service. And this is a good thing because you might want to use this operational data as preconditions during your for your delete steps. And once you've put that outside of your service, you also want to put your plan into the same model. Putting your plan in the same node as your custom operational data will bundle all of your operational data together. So now you have separated all of your operational data from your config data. Another benefit you get from putting your plan in your custom operational data node is that NSO will automatically create and delete that node, so you don't have to deal with it by yourself. And this is pretty simple to putting the plan somewhere else. It's just there is a parameter for a Nano service where you provide a path to where you want to put your plan. And under that node where you want to put your plan, you import the models that are provided by NSO. So you just point your Nano service plan to that location, and then everything will automatically end up there, handled by NSO. So put your plan into your custom operational data node. And then, of course, you want to keep a consistent service design pattern. So if you're using Nano services, you want to use Nano services on all of your services, both on CFS and RFS. You also want to have the plans outside of your services in the same way. You can use the same naming convention for the node that you put your plans in, maybe like service name -data or something like that, because that sets the expectations. You know what to expect. You have the same thing happening on your CFS as on your RFS. And use stacked services. The way FastMap works is that your service will rerun all of the code, all of the config generating logic for each time you redeploy. And you redeploy a service every time you make a modification to the service intent. This means that every time you make a modification to your service intent, all of the code will run again, and all of the logic to generate the service diff will be run again. So it's a good idea to chop this up into chunks. And a good idea is to do this into one device per service. So if I have a service that is going to configure multiple devices, I can stack these and make this service create multiple services instead. And each of these services will configure one device. Because if I make a modification on this service that is handling all of these devices, and this modification is only touching one single device, then I don't need to recalculate the diff for all of the devices, because the top service will only generate a diff that ends up on one single service that is changing that device that I want to change, and only this service then will redeploy, not all of the other services that are handling the devices. So you will have less code less config being regenerated. And now when you have more modularized packages, you can use the reloading single package mechanism with NSO. And if you have stacked your services, you can utilize converge on redeploy. Converge on redeploy is a setting that you can enable on your Nano service. With this, if you create your Nano service, the intent will be created in the first commit, but it will not be deployed. So a second transaction will be scheduled to redeploy your service. So if you enable converge on redeploy on your bottom services, and you create them from your top service, then your top service will create all of the bottom services in one transaction, but only the intent will be created in this transaction. Then a separate transaction for each and every service will be scheduled to redeploy the service and generate the device. And with this, you will get non-atomic behavior, even if you set your atomic setting on your commit queue to true. With this, you can also achieve higher throughput because you get more parallelism. And you can also use rollback on error, because rollback on error is not supported when you have non-atomic commit queue. But now you get the non-atomic behavior and you have the atomic set to true, so you can have rollback on error. But it introduces more asynchronicity. And with more asynchronicity, you get further away from network-wide transactions. Okay, so let's see our best practices in action. For this, I have created an LSA setup with one CFS and two RFS nodes. I have created a service on the CFS and I have two services on the RFS. My top service on the CFS, which I call link CFS, will create a service on the RFS. That service is link RFS. This link RFS is a stacked service, and this is the top service. So this link RFS service will create a link router RFS service. Let's just quickly go through the Yang files to see the best practices in action. Here I have the Yang file of the link CFS. If we scroll down here a little bit, we see I've put everything inside a container that I call link CFS. I've created my custom operational data that I call link CFS data. I'm using the plan data here. So I import the right models under my custom operational data node. And I've also modeled some custom operational data that I want to use. In this case, I have a list of RFSs. In my list of RFS, I have a list of devices, and I want to show the status of each and every device. This will show the commit queue status, the last commit queue item for this specific device related to this specific service. The status, we will see it here. We will also see if we have transient error for this device. And we will see when this was updated. We will see if something failed, the reason for failure. And for transient errors and retries, we will see the number of retries. And as you can see, this is outside of my service. My operational data node starts on line 43 and it ends on line 88. And then as a sibling, we have the link CFS config node. This is the service point we have here. So here we can see all of the service input data. It's just simple input data that will be passed down straight to the device. So nothing interesting to see here. And then if we scroll further down, we will start to see our Nano service declarative model. So we have our plan outline that shows us how the definition of our states. We have a couple of states here. We have one component called self with init and ready init. Then we have our custom component. We call it VLAN link. So basically the service will create one VLAN link for each RFS node it has to configure. There are a couple of states inside here as well. But this is the interesting part. So in NCS init, I have on delete a precondition. And this is the precondition that I need so that my CFS service is not backtracking before my RFS services has backtracked fully, which means that our delete configurations that are being pushed to our devices has actually been pushed to the network before our services are completely deleted. To be able to achieve this, I have to put this precondition on the delete state, on the init state on delete. And here I am monitoring my custom operational data, and I am basically checking whether or not everything is cleaned up. In this, and the custom operational data is actually updated by some kickers that I have implemented. It's in the same package. I'm not going to go through that code, but just briefly, I'm going to mention that these are notification kickers that monitor notifications that come from the RFS nodes. They will invoke actions that read the notifications and update this custom operational data with the relevant information. And this precondition here is monitoring this custom operational data. Then also down here, we have our behavior tree. And the interesting part here is the plan location here. So the plan location is pointing to our custom operational data node, the one we call link CFS-data. And then here is just how our service will behave once we create it. Not so interesting for what we are discussing at the moment. And then let's look at the next layer of the services. This is our top RFS service. And same thing here, I have put everything inside a top container. I call it link RFS. And under that, I have the list which represents the custom operational data. For this service, I don't have any custom operational data, so I've only put the plans in there, as you can see here. Same thing here, this is outside of the service, so we see this list ends on line 33, and then on line 35, our service model starts. We have our service point here, input config data, and plan outline, our states here. Same thing here, we have to monitor the bottom service that this service will create, just to make sure that the service doesn't disappear before our bottom service has actually finished backtracking. And same thing here as well. We point our plan location to our custom operational data node. And then if we look at the bottom RFS service, which we call link router RFS, same thing here, everything is in a container, and we have our custom operational data node, we have our service node, and we have our plans. But the interesting part here is the converge on redeploy flag that I've set here in the behavior tree. And this is where we enable the converge on redeploy on our service. And this is the only service I have enabled converge on redeploy on. And that is so I can achieve parallelism between these router services. And also, since these router services are the only services or are the services that are going to touch the devices, I want to have this converge on redeploy on these services so that I can achieve one device per commit queue item. Also note that for each and every custom operational data node, I have the same naming convention. So I have the service name -data. Take a look at what it looks like when I'm using these services. Here in my top terminal, I have my CFS. And on the bottom terminal, I have my RFS. On my CFS here, I'm starting by creating a service. So I have a template already prepared for this. I load merge it, link CFS example. I do a commit dry run. I see here that I will create my service with some input data. It wants to configure 3 devices, EX0, EX1, and EX3. My service will figure out which RFS nodes these 3 devices belong to. But I can tell you now that EX0, EX1, they belong to RFS1, and EX3 belongs to RFS2. So I commit this. And now when I commit this, I see that things are happening down on my RFS node. I can look at the plan of my top service. Link CFS data, test 1, plan. I see that the plan is finished. I can take a look at my custom operational data model. I have RFS nodes, lower NSO1, lower NSO2. Let's just look here. I can see that my devices has completed. On lower NSO1, I have EX0, EX1 completed. On lower NSO2, I have EX3 completed. Status completed. No transient error. They were completed at these timestamps. No reason, because there is no error reason, and number of retries is 0. So this is the custom operational data node that I populate with notifications that comes from the RFS nodes. Now, just to experiment a little bit with this, we can turn off a device and see what happens if I make a modification. Let's just verify our commit queue settings. Show devices, global settings, commit queue. We see that we have atomic set to true, unlimited retries, and the error option is rollback on error. And the same thing on our RFS. Show devices, global settings, commit queue. Same thing, unlimited retry, rollback on errors. So now I'm going to make a modification to my CFS, set link CFS test 1. I'm going to just update one of the values, unit. I set it to 20. Commit dry run. We'll see that it will touch device EX3. It will touch device EX1. And it will touch device EX0, which is the device that I've turned off. So now when I commit this, I expect to have a commit in the queue for this device that will just keep retrying because I have unlimited retries. I commit this now. Let's take a look at my operational data. So EX1 completed, EX3 completed, EX0 is executing. And if we look at our RFS, let's take a look at the commit queue. Run show devices, commit queue. I have a commit in the queue. It is still executing. We saw also that we got an alarm telling us that the device is unreachable. So the first time NSO fails to connect, you will see this alarm, but that is considered a transient error. And I have set retries to unlimited, so NSO will keep retrying for transient errors. And we can actually see that in our top operational data model as well. So now we see that it's still executing and we have a transient error. Number of retries are 5. And now I'm going to turn on my device again. So now I've turned it on and boom, there we go. Commit was completed. So far, so good. Now let's look at another case. Let's look at what happens if my commit is actually failing. So I will turn off my device again. But this time I will set my global settings, commit queue, retry attempt. I will set it to 0. So fail as soon as connection fails, which means do not retry. Same thing on my bottom node, commit, and I make a modification again. I will update my unit to 100. Commit dry run. Same thing here. EX3 will be touched, EX1 will be touched, and EX0, so all of the devices. And EX0 is the one that I have turned off. So I commit this. Let's see what happens now. Let's look at the data. It is still executing. And now it's failed, and it completely failed. We can see here the commit queue item failed, or the device here failed, with this reason. So let's take a look at our RFS and see what happened. If you look at our run show devices, commit queue, completed. Let's take a look at our completed list here. So as you can see here, all of the items only contain one device. One device. So if we wouldn't have had our services, bottom services on converge on redeploy, then we would have had all of our devices in the same commit queue item. So let's see here, EX1 completed, EX0 failed. Aha, okay, so it failed. So let's take a look at our, the diff that it was supposed to generate here, EX0. I was supposed to set unit here, config sys interfaces interface, ETH0 unit should go from 20 to 30. So let's take a look at what it is in the NSO database. So we do show devices, device, EX0, config, sys, interfaces, ETH0, interface, ETH0, unit. Unit is still 20. So it rolled back. But if we look at our service intent, show the bottom service one, link router, test one, which is the name of the service, EX0, which is the name of the device. The intent is 100. So if I request, if I try to redeploy this service, link router RFS, EX0, reactive redeploy. Let's do a redeploy dry run just to see. Dry run. We see that it will try to set it to 100 again. If I would redeploy this now, it would fail again, and we will roll back to the same state because the device is down. So let us turn on the device again. And we reactive redeploy it. There. So let's look at the config now. Unit is 100. And we look at our commit queue. Run show devices commit queue. Nothing in the commit queue. Let's take a look at our top CFS custom model. Got updated. All right, so now we've looked at the create and the update cases. Let's take a look at the delete case. For this, I will set my retries to unlimited again. Set devices, global settings, commit queue, retry attempts, unlimited, commit. Same thing on my RFS, commit. And now I will turn off my device again, EX0. And then I will delete my service, delete link CFS, commit. And we see things are happening. If we look at our plan, or we look at our custom data, let's start with the custom data here. We see EX0 that I turned off is still executing. Now it has retried also. And if we look at our plan, like this, the plan is still there, even though my service is gone. There is no service intent. And if we look at our zombie, we see that we have our zombie reference here. So this is a nice way to keep the service, a service reference remaining while your system is cleaning up. And if we turn on our EX0 device now, and we wait for a while until it retries again. There, it retried. Zombie is gone. Plan is gone. Everything is gone. And with that, we have supported all of the cases, create, update, delete, by using our Nano service best practices. And that's all I had to show you. Thank you for listening.